Okay, so today we're going to talk about bonding. And there are three types of chemical bonding that we're going to ultimately know from this class. Metallic, ionic, and covalent. And when we were talking about water last time, the type of bonding involved there is actually covalent bonding. And so we'll go ahead and define that right now. But we really want to spend most of today getting started with ionic bonding. So this is really just an introduction to ionic bonding that we're going to have today. Now one thing, we won't discuss metallic bonding today, but we'll get to it eventually, okay? It's an important type of bonding that we'll also need to know. So, first off, bonding. Okay? And then two types of bonding that we'll be discussing today. So the first one is covalent. So covalent bonds form when two nonmetals, and I'll underline that because they have to be nonmetals, okay, share, and they have to share it, okay, one or more pair of electrons. Okay? So, nonmetals sharing electrons. So let's go back to the structure we looked at yesterday. Okay? Or, sorry, last time. So, hydrogen and oxygen were the atoms involved. And we were talking, of course, about...
Water.
Right. Which molecule were we talking about?
H2O.
H2O, or water, right? Okay, a bunch of us are answering. Good. So water looks like this. You can draw water like we did last time. H dot dot O dot 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 H. Each dot represents a valence electron, and the two dots here and the two dots here represent each a covalent bond between one hydrogen and one oxygen. So this hydrogen is making one covalent bond with this oxygen that also makes a covalent bond here with this other hydrogen. Okay? So these electrons on top and bottom, these are called lone pair electrons. And we'll talk more about what this structure is. It's called a Lewis dot structure. We'll talk more about that later, but for now you can just write down lone pair electrons. Oxygen has two lone pair, and it's also got two bonding pair that it shares with two different hydrogen atoms. Okay, so these are covalent bonds. And they can also be drawn in a different way. I can actually draw water like this, HOH, with the lone pair shown here, okay? And again, these are the covalent bonds. Now they're represented not by two dots, but by a single line, okay? Each covalent bond represented by a single line, and that's okay too, okay? So this is a Lewis structure. We'll call this just a proper Lewis dot structure, okay? And the differences and the nuances between the two we'll discuss at a later date when we really start to get into organic chemistry, but it's good to see this now. Okay, so that's what's going on with covalent bonding. So ionic bonding is a different thing, okay? Ionic bonding is very different. So ionic bonding, or ionic bonds, form when a metal, I'm underlining metal, donates, and it has to donate one or more electrons to a nonmetal. And that's essential too. Okay? So the metal is donating one or more electrons to a nonmetal. That's actually what's happening. And so there are probably a couple chemical formulas that we know off the top of our heads, right? One of them is water, H2O. Another one is probably the chemical formula for table salt, okay? Table salt. Who can tell me the chemical formula for table salt? Okay, a bunch of us know, right? NaCl. So let's look at that as an example, okay? Here's an example. NaCl otherwise known as table salt. Okay? And this is the only rock that humans eat on a regular basis. I think there are other salts you could eat. I think you could eat some magnesium chloride or something. Don't quote me on that, but maybe I'm sure you could eat potassium chloride. That wouldn't be bad for you. But like this is really the only rock that we eat in large quantities. And so like if you have a few grains of salt, right? What you're actually doing is like eating a rock. Okay, those are little like salt crystals, right? That you're eating. They look like, if you look at them under a microscope, they look like little mini rocks. Okay, and so this is a rock that we eat, and it's a rock that we need in order to live. So we wouldn't be doing too well if we didn't consume a reasonable amount of sodium chloride is what we end up consuming. Okay, so we need this chemical for our existence, just in all practical sense. I mean, I'm sure there's some way you could get around that. But like sweet mercy, that'd be awkward. So like humans need to eat this to survive. Just take that at face value. And so we need this stuff, right? And it also helps our food taste a little bit better. So we'll be watching a documentary series called Salt, Fat, Acid, Heat. And the first episode of that is salt, right? And we're going to learn how salt is made. And we'll actually make some salt ourselves. In fact, we might actually do that before we get into the bread baking, even though we're investigating bread right now. That might end up being a bit of a tease before we actually do salt, and then bread later on when we start really talking about covalent bonding in depth. So, okay, so what's going on with sodium chloride? So I want you to look at sodium over here, and then chlorine is right over here. Okay, so how many, and you can, one good thing to do right now is to take out your periodic table. So if it's folded up in your notebook, I would go ahead and take it out, because we're going to have to talk about these two chemicals. Okay. So sodium, right? We'll start with sodium. Sodium has how many electrons? 11. Okay. And let's think about something, right? So like here's argon. Here's argon. Argon has how many electrons? 18. Now, if sodium wants to become like argon, how many electrons is sodium going to have to pick up? 7 electrons to become like argon, okay? So if you look at this, sodium would have to gain 1, 2, 3, 4, 5, 6, 7 electrons to be like argon. That's a crazy number of electrons, okay? I'm going to tell you right now, all right? Nobody's doing that, okay? Nobody in this periodic table is doing that. The elements don't do that. They don't pick up 7 electrons to become like something else. That just doesn't happen, okay? At least not with any chemistry with which I'm familiar, which we're going to see on a regular basis. There might be some funky, transition metal thing that happens like that, but I don't know of it if it exists. But I'm telling you right now, the main block elements for sure are not doing things like that, okay? They don't do it. So sodium's not going to try to pick up a bunch of electrons and become like argon, right? So when metals can participate in ionic bonding, what do? They donate 1 or more electrons, right? So look, sodium has 11 electrons. What nearby, in terms of atomic number, nearby noble gas has only 1 fewer electron than sodium? Aha! So when you're talking about something like sodium, and some people think the periodic table should be more of a periodic cylinder or a periodic spiral because of this. See, one of the things you lose when you flatten this representation out is your sodium's all the way over here, but he's actually electronically just 1 electron away from neon, which is over there, right? So you're sort of separating these two things that actually have a lot to do with each other. So when sodium bonds, it doesn't gain 7 electrons to become like argon because they're in the same row on the periodic table. Sodium doesn't know about the periodic table. Instead, sodium loses 1 electron to become like neon, okay? So here's what happens in this chemical, right? Sodium loses 1 electron to become like neon, okay? And then if sodium is losing an electron, right, what does the nonmetal do? What does the nonmetal do? Gains an electron, okay? So if chlorine gains an electron, who does it become like? Argon, okay? So sodium loses an electron, chlorine gains one electron to become like argon, okay? So in summary, for the chemical itself, what we'll say is sodium donates one electron to chlorine to form sodium chloride. Okay? And that's the scoop. So that one example will get us started with ionic bonding. And we're going to spend a few lectures on this. We might spend a week and a half or so learning about ionic compounds. And we'll end up taking a quiz on ionic compound formulas and naming, called nomenclature. Okay, so when we talk about the naming scheme for something like a systematic way to name the different ionic compounds that can exist in nature, we talk about the nomenclature, so we say ionic compound nomenclature. So we're going to take a quiz on nomenclature and formulas for ionic compounds in a week or two, just whenever we're ready for it, okay, no rush. And so we're going to be studying salt over the next few weeks once we're done, or sorry, just as we extend from here. So we're headed in that direction, okay? So that's all for today, but we still have some questions left. So we have a one salt here, sodium chloride, but what about magnesium chloride, or potassium fluoride, or calcium oxide, right? There are many different ionic compounds. We'll have to develop a firm understanding and a general understanding so we can know what's going on with any of them arbitrarily. Those things we will begin to discuss next time. All right? So that's all for today, scholars. If you have any questions, let me know. Otherwise, you can put your notebooks away.